This video is going to talk about how science sometimes talks to us, or we read science and we think it's an absolute fact just because some smart people work with it. What I'm going to talk about today is a very common uh, situation that you experience, and I'm going to talk about it in terms that you don't experience. And then we're going to talk about the first explanation of that theory and why they're still arguing about it today. Doppler effect. You sense the Doppler effect when a siren goes by you. When that siren goes by you, it sounds like that the siren producing mechanism, producing that tone, is changing as it goes by you, as if it could sense that it's going by you, so that the guy inside the car automatically changed the tone just to make that happen. Nope. I think you know that the siren sitting still, as we're just sitting still by that siren, is going to be the same tone all the time. And somehow it seems to be changing. This is wave stuff. Waves are make up sound, and they're little vibrations in the air, compressions and rarefactions in the air. So, what can we do to figure out why that happens? Okay, that's the thing that we experience all the time. The other experience that we don't have a good way of relating to is the fact that stars show a red shift in some cases. And that red shift means that the frequencies, if that star was sitting still in relationship to us, would uh, be a different, quote, color. In other words, the light that's coming off of it would be made up of light that is uh, not as much red as when we detect that it's going real fast away from us. Sounds like the same thing, doesn't it? Well, it's not. And I'm going to go through a little bit of math here to see if we can figure out what the controversy is about this. Okay, let's try to do some facts and figures here about the siren that we hear, and how that siren starts out at a high tone. And that's as it goes by. It maintains a high tone, and then it goes down. So here's the police car. Here's a police car, a little nice little red light there. And I'm setting the siren as 1000 hertz just so we can do something as a comparison. And here's the sound of the siren. Not very interesting siren, but that's my siren. And we're going to compare this from when it's standing still to when it's moving. Okay, we'll turn that off. That gets kind of irritating. Anyway, I've laid out this setup here where I've got a little guy over here, that's us, and 1020 meters. And there's a reason why I chose 1020 meters. And here's the car. So we're 1020 meters away. That's like 10 football fields, let's say, close to that, or something like that. It gives you an idea. And the speed of sound is 340 meters per second. So sound moves at 340 meters each second, which means each second it goes about 3 football fields. This is about 10 football fields. This goes about 3 football fields. So the reason I chose the 120 meters is because if we multiply 3 times 340, we get 1020. So that means as soon as this siren starts, if it's quiet and it starts, the noise doesn't reach my ear until 3 seconds. 1, 2, 3. Then it reaches my ear, that tone of 1000 hertz. Now, there's a certain characteristic of sound that will help us figure out how this Doppler effect works. And let's see if I can sketch a little bit there. There is a thing called, let me use blue. Blue is a lot nicer. Let's go to blue. And then I want to show you that, what was it I was going to do? Lost my train of thought. Oh, I was going to do some little drawings here. This is the Greek letter lambda. And the Greek letter lambda is the wavelength. So there's waves of sound going through air, that 1000 hertz, and the wavelength of that is going to be equal to, let's see what it's equal to. It's equal to the velocity of sound. I'll just put an S there for sound. The velocity of sound over the frequency. So if the car is standing still, the car is over here and it's standing still, how long does it take? Boy, this cursor's kind of going crazy. Anyway, goes over here, and the velocity of sound divided by the frequency is going to tell us what the, here, let me draw a little picture here again. Here's the 1000 hertz, and the wavelength is going to be from here to here, and I'll put little arrows there to show the distance between the wavelength. This is a wave of air going through there. I've got it represented by a sine wave. So this wavelength is going to be equal to, it's got to be pretty tiny, but the velocity of sound is 340 meters per second. And that's going to be divided by the frequency, which is 1000 hertz. It's going 1000 cycles per second. And what do we get when we do all this calculation? Let me see. I can actually take the time and get the calculator out here and see how I'm figuring that out. Where's the calculator? It's going to show up here eventually. Okay, let's see what it looks like. That's going to be 340 meters per second. And that says that if I divide that by 1000, then that says each cycle is going to be 0.34 meters. So if I bring this down, I put another equals sign here. That's going to be 0.34 meters. So if you can think about it, 0.34 meters of sound, there's going to be several of these 1000 hertz things that are moving across here before it hits my ear. Now, one thing to think about is this is just kind of like relativity in a way. If the sound starts here, I don't even know that it occurred for 3 seconds. So what I'm looking at, or what I'm not looking at, but what I'm hearing is the past. I'm hearing the past thing that happened with this siren. And as long as the car ain't moving, looks like it won't be because it doesn't have any wheels, but as long as the car is not moving, all I hear is that constant tone. And if the tone goes up, I hear it. If the tone goes down, I hear it. But if it's just a single tone, then all I hear is just that single tone, and that's it. So let me think about this for a while. What happens if the car is moving? Then we got a whole different thing to talk about. So if you've absorbed this, I will kind of clear the board here a little bit so I can make up some other things that have to occur. Okay, we covered the stationary situation where we had a 1 kilohertz tone, and let me dial it in here. Sorry for the delay. 1 kilohertz tone. That's approximately 1 kilohertz. Let me get it up there exactly. Let's be exact about this. There's the 1 kilohertz tone coming from a stationary object, so it's all the same. What I'm going to propose is that we have this turned on for just 1 second. 1001. We send that pulse, and it takes a while to get, actually about 3 seconds or so, to get to the other end of that. We've got this thing spread out over 1,000 meters, so it's taking a lot of time. Now, if I have a 1 kilohertz tone, the wavelength of that 1 kilohertz tone is going to be 1,000th of the speed of light, or 343 meters. So 1,000th of 343 is going to be about 0.34. Let's see, where's 334 meters? 0.34. Okay, that's going to be 33. Okay, that's going to be about like that on the meter stick. There's the wavelength for that 1 kilohertz tone. So it's moving pretty quickly along the line. Now, what about the car? Well, I'm going to propose that the car is going about 80 kilometers an hour. That's about 50 miles per hour. So 80 kilometers per hour, if you do the little math thing, you come up with 22 meters per second. That means that in 1,000th of a second, at 22 meters per second, you'll be going at 0.02. You would have traveled 0.02 meters. So let's see where it is. 0.02. This was 0.3 meters. This is 0.1 meter. This is 0.0. So we just have that little bitty piece there. So it travels that distance in that much time. So this wavelength, which was 0.343 meters, is now chopped down to about 0.318 meters. 0.318 meters is a different wavelength. And in sound, that different wavelength, as it goes smaller, that means the tone goes higher. And if we do the math, that comes up to about 1,069 hertz. And let's see if I can dial this in fairly quickly. No, this thing doesn't dial it in that fast. If you have perfect pitch, you know what the 1,000 hertz is. Here we go. So that was the 169. Here's the 1,000. In other words, oh, I went overboard. So it's going to be a higher tone anyway. I wish I could have a sliding sound thing. That would be a lot better. Let's shut that off. That's irritating. Okay. Now, we have that, that means that those waves are going to get squashed down as that car moves. But they're still going to be moving through air. But how fast are those waves moving through air? How fast are they moving? One way to look at this is the waves have a 22 meters per second boost before they get moving. So, before they get moving. So that's going to mean that actually those waves are going to be moving faster than the speed of sound. Is that right? I think that's right. We'll have to look at the math to be sure. But on the other end, it's going to see that 1 second tone as with these squashed waves, it's not going to last as long. It's only going to be about zero point 0.9 seconds. So that's the rough qualitative look at this whole thing. Now we're ready for some math. Okay, now for some math with the police car moving. So let's first go up here and let's see. I'll take black and I'll put some wheels on the police car. Looks like it's got a lift kit or something like that. So, as I said before in my little talk, the police car is now moving this direction towards the person here that's stationary, and it's moving at 22 meters per second. And let's see what kind of mass we have. If it's moving at 22 meters per second in, as I said before, in 1,000th of a second, that means it's going to be moving at it's going to move 0.022 meters. Whereas the rest of this thing is going to be moving at 0.34, actually it's 343 meters down here. So if we compare those two wavelengths, here's the 3.4, nope. Let's get my little eraser there. Get rid of that point. Come up here to the marker. And that's going to be 0.343 meters between these 2 points. And what's the police car? Let's change the color so we can kind of associate that. The police car between that 1,000th of a second is going to be moving this little piece of it, which is, I'll draw the arrows outside, between these two little blue things, is going to be moving point, what did I say, 0.022 meters. So that means we've chopped the wavelength down from 0.343 to 0.022. And how do we calculate that? Well, we just take 343.343, and then we subtract the 0.022. Let's see, 22. Let's see. Let's make it 0.022. Got all the decimals lined up there. And what does that give us? 3 minus 2 is 1, 2, 3. So we chopped it down from 343 to 321. Now, what kind of frequency does that mean? What kind of frequency is 0.321 as seen by this observer? Well, 0.321, if we use this kind of relationship and change it around for frequency, let me clear up some of this screen. Well, I think I can make it down here. So what I'm going to do is come over here and say frequency, is equal to the speed of sound over the wavelength. So speed of sound, that's going to be 343 meters per second. And then we divide by, what do we divide by? 0.321. Okay, so that should explain it pretty well. Next, we're going to see if we could do the same thing with light. And that's what this whole thing is leading up to, is light. Does light work that same way? If you have some star or stellar thing that's moving towards the Earth at near the speed of light, or enough speed of light that it's going to affect it, is the same thing going to happen there? The problem I think we'll find is that speed of light is a constant, always, always.